All right, now we're going to deal with the even odd identities. So the even odd identities are just talking about what happens if you had like a negative angle. How could I express that in terms of a positive angle? So um, I'm going to cover the sine, tangent, and cosine versions of the even odd identities. And I'm going to count on you guys understanding. If you guys understand that, you should be able to make sense of the cosecant, the cotangent, and the secant versions of the negative of when you have like a negative input. Why that would be true? Because it's yeah. Okay. So according to the even odd identities, it is saying that when I see sine of negative theta, that should be the same as negative sine of theta. Okay. But why though? So to look at this, I would recommend that we go back to the unit circle, right? So let me go ahead and pull up the unit circle for this. Okay, so here's the unit circle. Now let's make sense of why sine of negative theta would equal the negative sine of theta. So here's what we notice. When I see a negative angle, I think of it as a rotation in the like a clockwise rotation. So let's say I rotate, I don't know, um 60 degrees clockwise. 60 degrees clockwise would take me here to 5 pi over 3 if I rotate clockwise. I'm sorry, counterclockwise to represent the positive rotation of the angle. It would take me here. So if we're talking about sine, sine refers to the outputs of the y values. So we're looking at radical 3 over 2 and negative radical 3 over 2. So sine of negative pi over 3, 60 degrees, would be the same as negative sine of pi over 3. Okay? Well, I know this value represents negative radical 3 over 2 according to the unit circle because it's that value right there. And that should equal negative sine over sine of pi over 3 would be radical 3 over 2. So as a result, I get negative radical 3 over 2 is equal to negative radical 3 over 2. So that's kind of showing you that it works, but notice it works because of the symmetry of the unit circle. Rotating clockwise means you're rotating with a negative angle. So the amount you rotate from the x-axis is the same, but the only difference is instead of going counterclockwise, you'd be going clockwise. That's what makes it negative. So the reference angle is still the same, but now you're going the opposite direction. So that's why, since you're going in that opposite direction, this opposite manifests itself as the negative version, as if you're going in a positive direction, right? So that's why that's true for the sine. Now, if I take a look at the cosine, because we'll talk about tangent in terms of the quotient identity, and that kind of shows you how, one, I use identities to prove other things, and why these are going to be true. All right. So for cosine, I'm told that cosine of negative theta is the same as cosine of theta. Okay. So let's use a specific example to try to generalize this. So let's say I rotate 2 pi over 3, right? Well, actually, I should start with the negative version. So let's say I rotate negative 2 pi over 3. So that will take me here to 4 pi over 3 if I were going in a positive direction. And that would be the same as if I rotated this way counterclockwise, right? So again, the negative just means you're rotating clockwise instead of counterclockwise. And we're talking about cosine, so we're looking at the x values. So there's that, and there's that. So according to this specific example, cosine of negative 2 pi over 3 is the same as having a negative half. Okay, and this is saying that's going to be the same as if you just took cosine of 2 pi over 3, and that'll give you a negative 1/2, which is true. And again, this has to do with the symmetry built into the unit circle. So in this instance, when we rotate and we look at the x values, aka the cosine values, well, because we're still rotating clockwise or counterclockwise, it doesn't matter because the x values are still going to be the same, because we're going to go from positive to negative. Either way, we go from positive x values to negative x values. If we go from the 0 degrees to whatever degrees, right? If we rotate clockwise, the x values will start at 1, then start to decrease, turn negative. Okay. If we go counterclockwise, we're going positive. Okay, still positive, but it's going to decrease. Then I get negative. So that's why that's true. Okay. The x values change from positive to negative no matter which way you rotate. So now let me show you how to use some of these trig identities. So we're going to use the fact that I know that sine of negative theta is equal to negative sine of theta, and that cosine of negative theta is equal to cosine of theta. So that's what I know. And I am told that, and I know that tangent of theta would equal sine divided by cosine. So if I use these pieces of information, it doesn't take too much work to show that tangent of negative theta should equal negative tangent of positive theta, right? Because I can just replace this with sine of negative theta over cosine of negative theta, right? And I know that sine of negative theta is the same as having a negative sine of theta, and cosine of negative theta is the same thing as having a cosine of theta. And as a result, if I focus on this part right here, well, that's just tangent according to the quotient identity. So I can end up saying that this should give me a tangent of theta from this box right here, and it's negative because of that negative that was out there to begin with. That's how I can prove that would work. And that's what identity, like when I ask you to work with identities, that's what it looks like. You use some basic facts, you do some substitutions, and you work your way down to prove that the one statement would have to be equivalent to the other.